Have you ever wondered what happens inside a black hole? This question has haunted the minds of scientists, astrophysicists, and curious thinkers alike for centuries. Black holes, these seemingly insatiable cosmic entities, have long been a source of fascination and mystery. In the grand tapestry of the cosmos, they stand as enigmatic anomalies, their general properties as intriguing as they are elusive. It was the unparalleled genius of Albert Einstein who first proposed their existence, his theory of general relativity painting a mathematical image of these infinitely dense points in space-time. Yet even with this theory, the full nature of black holes remains a puzzle, their invisible borders, event horizons, concealing from us what truly happens within. This profound curiosity, shared by the scientific community and beyond, has sparked a relentless quest for knowledge. A quest to decipher the enigma that is the black hole. So let's dive into the depths of these cosmic mysteries and explore the top breakthroughs in understanding black holes. Our journey begins with an extraordinary man named Carl Schwarzchild and his revolutionary solution. Schwarzchild was a German physicist and astronomer who, despite serving in World War I, managed to solve Einstein's field equations. His work led to a groundbreaking concept in astrophysics, the event horizon. This invisible boundary around a black hole marks the point of no return, beyond which nothing, not even light, can escape. Schwarzchild didn't stop there. He further defined the Schwarzchild radius, a critical measure that determines whether a celestial body will turn into a black hole. If an object's physical radius is less than its Schwarzchild radius, it will collapse into a black hole. This concept opened up new horizons in understanding black hole formation and their enigmatic nature. Schwarzchild's work was truly revolutionary. It not only provided us with a detailed mathematical description of black holes, but also laid the groundwork for all future research in this field. This marked the first step toward understanding these cosmic beasts. Next, we turn to the groundbreaking work of Roger Penrose and Stephen Hawking. These two luminaries in the field of astrophysics proposed the Singularity Theorems, a set of principles that proved the existence of singularities under general conditions. Singularities are points in the universe where gravity becomes infinite, and our understanding of physics breaks down. It's like trying to divide by zero on a cosmic scale. Penrose and Hawking's work showed that under certain conditions, singularities are inevitable. These theorems have profound implications for two major areas in astrophysics. First, they support the Big Bang theory, suggesting our universe started from a singularity. Second, they predict the fate of stars. Massive stars at the end of their life cycles collapse into singularities, forming what we know as black holes. The singularity theorems are more than just equations on a page. They represent an audacious leap in our understanding of the cosmos. This work fundamentally altered our understanding of the universe. Then came a discovery that seemed to defy the very nature of black holes. Stephen Hawking, a name synonymous with black hole research, made a prediction that challenged our understanding of these cosmic anomalies. He proposed that black holes were not simply vast, timeless voids, but rather they were slowly evaporating due to quantum effects. Here's how it works. Quantum mechanics, the strange rules governing the smallest particles in the universe, allows for pairs of particles and antiparticles to spontaneously pop into existence near the event horizon of a black hole. One falls in, the other escapes, and voila. It appears as if the black hole is radiating. This is known as Hawking radiation. It's a slow process, mind you. A black hole with the mass of our sun would take longer than the current age of the universe to evaporate completely. But the mere possibility turned the classical view of black holes on its head. This opened up a whole new field of black hole thermodynamics. Fast forward to the 21st century, where a new window into the universe was opened. Enter the era of gravitational waves, ripples in the fabric of space and time caused by some of the most violent and energetic processes in the universe. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected these waves for the first time. This wasn't just a blip on a screen, but the echo of a cosmic cataclysm, the collision of two black holes. This detection confirmed what Einstein's theory had predicted and revealed a new method to observe the universe, opening up a new way to see black holes. The detection of gravitational waves has profound implications. It allows us to test general relativity in extreme conditions and observe cosmic events that would otherwise be invisible. It's like gaining a new sense, a new way to touch the universe. This brought us one step closer to seeing black holes up close. Finally, we arrive at a moment that will be forever etched in history. A pivotal moment that brought the once elusive black hole into the realm of the observable. The first image of a black hole captured by the Event Horizon Telescope, a global network of radio observatories working in unison, was revealed in 2019. This image was more than just a picture. It was a testament to the power of human curiosity and ingenuity. It was a direct test of our understanding of black hole physics, and a confirmation of the predictions made by Albert Einstein's general theory of relativity over a century ago. The image displayed a ring of light surrounding a dark region, the black hole's shadow, against a backdrop of hot gas swirling around it. It was the silhouette of a supermassive black hole, lurking in the heart of galaxy M87, 55 million light-years away. With this, the once invisible became visible. So what's next in the realm of black hole physics? As we march towards the future, two major potential breakthroughs loom on the horizon. First, the resolution of the information paradox. This paradox, a consequence of quantum mechanics and general relativity, has puzzled physicists for decades. It's about whether information that falls into a black hole is truly lost forever, or whether it can be retrieved. A solution to this could revolutionize our understanding of quantum gravity. Second, the discovery of primordial black holes. These are theoretical black holes formed in the early universe, mere moments after the Big Bang. Their detection could shed light on the nature of dark matter in the early universe itself. These are just the tip of the iceberg. The field of black hole physics is teeming with questions, waiting to be answered. It's an exciting time to be an astrophysicist or even just an observer of this fascinating field. As we continue to unravel the mysteries of black holes, who knows what we'll discover next?